Okay, so now we're going to use the formal definition of a limit. Let's take a look at this first example. Okay, when we do this, the first thing we want to do is we want to start by defining our function minus the limit, and that has to be less than epsilon. So what I'm going to do now is just direct substitution. In addition to that, we have to define that 0 is less than the absolute value of x minus our constant that we're going to approach, which is going to be less than delta. Okay, so when we do that, our function value is 2x plus 4. And right now, we start off our proof by just doing the scrap work. So that's what we're doing first. Minus our limit, which is 6, is less than epsilon. And here we have the absolute value of x minus 1 is less than delta. And the next thing I'm going to do is I'm going to simplify this statement. So I know that that simplifies to the absolute value of 2x minus 2 is less than epsilon. So it almost looks like this statement, and that's what I want it to do. Good, so the next thing we're going to do is we're going to factor out a 2, and by definition I can factor out the absolute value of 2, x minus 1, less than epsilon. I'm going to divide both sides. Technically, we're dividing both sides by the absolute value of 2. So the absolute value of x minus 1 is less than epsilon. The absolute value of 2 is 2 over 2. Okay, so the next thing we want to do is we actually want to choose that delta, that for every delta, or as we're approaching that constant, right, from the right and from the left, that interval is going to be for every epsilon over 2. So all of that was our scrap work in order to write our argument. So that's what we're going to do next. We're going to use our scrap work and we're going to write our argument for our proof. And our argument is that we're going to let epsilon greater than 0 be given. And then we're going to define our delta based on what we chose delta to be, which was if the absolute value of x minus 1 is less than what we chose delta to be, is epsilon over 2, then, and now I actually start showing my proof, the work I did in my argument. And the first thing we did was we took the absolute value of our function, then we simplified, and we got 2x minus 2. Then we factored, and we got the absolute value of 2, x minus 1. Okay, and this is less than, and our argument was absolute value of x minus 1 is less than epsilon over 2 for our delta argument. And I'm going to show that epsilon over 2, if I were to multiply that by 2, that is equivalent to epsilon. So now I know that the limit exists based on this argument. Okay. Now let's take a look at this example. Here we have some additional steps when we're simplifying. So we're still going to do the same thing. We're going to define our function minus our limit is less than epsilon. And we're also going to define our delta argument, x minus c, less than delta. And when I do some direct substitution, I get the following. So what I want to do is I want to work on this to look like this. So I'm going to go ahead and I'm going to factor the numerator, and that's x plus 2, x minus 2 over x minus 2 minus 4. So here I can see that these two are going to simplify. Okay, and then when I simplify that, I'm going to get x plus 2 minus 4 less than epsilon. And then I'm going to get x minus 2 is less than epsilon. So from here, this argument looks just like this argument. So I'm going to choose for every delta, I am going to choose an epsilon. And I'm going to write my argument. And this is what your argument would look like. So we're going to let epsilon greater than 0 be given. If here's our delta argument, then here's our work. And here, remember, we chose delta to be epsilon, so this makes this argument a little simpler towards the end. Okay, so let's take a look at this one. This one, we're going to actually have to do some bounding like we talked about in class. Pause the video, go ahead and try it. When you do direct substitution, you are going to end up with this. Okay, so from here, take a look at what we've done so far. We went ahead, we simplified, we factored. We're almost to where we want our argument to be equivalent to delta. However, here, I have the absolute value of x minus 2, which is what I want over here. I don't want this absolute value of x plus 2, so I have to start bounding. I do that by stipulating that delta be less than or equal to 1, and we're going to create boundaries by manipulating the absolute value of x minus 2, which is less than delta, and here we're stipulating that it's less than 1, so therefore I'm going to go ahead and I'm going to solve this interval, manipulate it so that it looks like this, and then I can do direct substitution. When we isolate the variable, we end up with this, and now I want this x to look like this x plus 2, so I'm going to go ahead and add 2 to everything, and I'm going to get 3 less than x plus 2 less than 5. So now I have what I've stipulated this to be. I always err on the side of caution by choosing this 5, and I'm going to go ahead and do direct substitution. When I do direct substitution, I end up with this, and I want to isolate this so that way I can choose my delta, and here it becomes very clear that the absolute value of x minus 2 is less than epsilon over 5, so I'm going to choose delta to equal epsilon over 5. So in our argument, we want to make sure that we say that, and it will look something like this. Okay, and then to conclude it, here's your argument. Let delta be at minimum 1 to epsilon over 5. If 0 is less than an absolute value of x minus 2 less than epsilon, then make sure you include all the work that you did here. For some reason, it's not letting me point. Okay, and that's it. So here we took f of x, our limit, we simplified, we factored, we got these factors, we bounded specifically x plus 2 to 5, and then we showed that what we chose for delta, which was epsilon over 5, by multiplying it by 5, it was equivalent to epsilon.